He is also an active open source software contributor for ML rappers and an avid technical writer on AI and technical in general. So yeah, welcome Vishwanan, and now the session is over to you.
Thank you, Dr. Rakesh. Let me share my screen. Is my screen visible?
Yes, yes.
All right, then I'll begin. All right, hello everybody. My name is Rishabh. Thank you so much for being here. I understand this is the last session of the day. Thank you for waiting and your patience. Today I'll be talking about a topic that I myself am researching at the moment. It's about understanding the expressiveness of graph neural networks. So expressiveness of graph neural networks is a very recent topic. It has picked up a lot of pace very recently, and a lot of people are now jumping on the train to find out, what exactly are graph neural networks, I guess, thinking when they make these predictions on graph structured data. So before I formally begin, a bit about me. Dr. Rakesh already mentioned a bit of this, but I'm an undergraduate researcher at the School of Computing at the National University of Singapore. I do graph deep learning, and I also have interests in self-attention mechanisms and transformers. I am an open source contributor to machine learning tools and machine learning model wrappers, and I also write technical articles on machine learning and AI. I'm also part of the teaching staff at a few machine learning classes at NUS, where I teach introductions to machine learning and AI. So this is a rough overview of what we'll be going through today. We'll start off with a very quick deep dive into graph neural networks, what exactly they are and how they operate. Next, I'll be taking you through a bit of algorithm theory, mainly on graph data or graphs in general. And then we'll get into a bit more into graph neural network expressiveness. And after that, I'll give you a quick literature review on what has been done so far. And we'll end off with some of my own comments. And we'll have a bunch of questions and answers at the end. So from computer science, I guess we're all aware that a graph contains a bunch of nodes that represent entities. So in a social network, they could represent users. In a molecule, they could represent atoms like the carbon atom, hydrogen atom. So when some of these nodes interact in special ways, they have some relationship between them. And these relationships are denoted or represented by these edges between these nodes. So the thing about graphs is that aside from what these nodes represent, these nodes can also contain a bit of extra information. So in typical normal machine learning, your data has features. In the same way, your nodes and edges can have features that either represent the entire graph or they represent each of these nodes. So in the context of social media graphs, these features could be age, gender, political inclination, and a bunch of information like the user bio and all that. And these edges could represent whether this user follows this other user. So given this graph here, let's zoom into this center node, this target node. And every node in a graph, it has these connections to nodes next to it. And we call these nodes the neighborhood of this node in the center. So if this node is some node I, all these nodes, the yellow, red, purple, and the orange nodes, they belong to the neighborhood of this node I. So when you have this neighborhood here, each of these nodes have their own features. So through this process called message passing, we take all of these features and send it to the target node. So you have some function G, we call it an aggregation function because it's aggregating all the neighbor features around the target node. It's collecting them all into one place. So from all these neighbors, J, the yellow, red, purple, and orange, we send it to this target node and we perform this function G. So you take all of these neighbor features, you transform them in some way, and then you update the feature of this target node in the center. So we have this function f, and we call it the readout function or the update function. What it does is it takes the target node's own features, and it takes the aggregated features, which we call a message. So it takes the message and the target node's own features, and it combines them in some way, and it updates this target node's features. So when you do this for all the nodes in your graph, right? You do it for all these nodes. You can do them parallelly, and once we finish doing this for all the nodes, we call that one entire round of message passing. So one round of message passing is the same thing as saying one pass through a graph neural network layer. So you can think of it as the forward pass through a multi-layer perceptron or any feed-forward network. It's the same thing. When you pass all these nodes through a single GNN layer, you will be doing one layer of this message passing. And every time you'll be updating the features or the embeddings of all these nodes in the graph. And if you have edge features, of course, you'll be updating the edge embeddings or the edge features as well. So as I mentioned, in some cases like biochemical data between molecules, some of these edges have meaning. So in molecules, they could be single bonds or double bonds. In that case, you can also have edge update functions that take in the edge feature as well as the node features for both of the nodes at the end of this edge. And you can combine them in some way, some function. This could be a feed-forward layer or some complex neural network that transforms this to give you the new edge feature. So you can think of it as the same message passing procedure applied to all the edges as well in the single GNN layer. So once you've done this a couple of times, once you pass it through a few layers in your GNN, you will get this final configuration of node features for all of the nodes and all the edges. So after that, you can, if you want, you can get this global graph embedding through this function called the global aggregation function. So you take all the node features from all the nodes in your graph, and you combine them and you put them together in some way using this function h, so that you, at the end, maybe you get one final vector u, and you can do a bunch of things with this u. So with GNNs, you can do quite a lot of things. Over here, suppose we have a lot of these nodes and each of them have their final features. You can stack all these features together and maybe pick one of these node features. You can pass it through a multi-layer perceptron or any neural network, and you can do node classification. So for example, this node, it could be, or this graph could represent a molecule. When you pass this certain feature vector for this node into a multi-layer perceptron, you can predict whether this is a carbon atom or an oxygen atom or a hydrogen atom because of the properties contained in the features. Similarly, you can do edge prediction, meaning I have this node over here, and say I have this gray node in the corner. I take both of their edge features, I put them through a multi-layer perceptron, and it'll give me a probability value between 0 and 1. And if it's greater than 0.5, I can say that an edge can exist between, this orange node and this blue node. An edge can exist between both of them. And this would be very useful in social media applications where you have a bunch of users and you want to recommend who to follow or who to connect with in the social media graph. So whenever this prediction gives a 1, then we can send the user, hey, do you want to follow this other person? Next, we can do whole graph classification. As I mentioned, you get this final feature vector, this graph feature vector, u, and you can just pass this u vector through a multi-layer perceptron, and at the end you can say, is this a graphene molecule or is this a H2O molecule? So that one is more of a whole graph. You take it and you classify the graph. And of course, you have your final or one of your other applications, graph autoencoding. So if you have a graph with a lot of noisy data, or you have a lot of corruption in your graph, you can pass it through an autoencoder, a graph autoencoder, and you can get the reconstructed graph that you can create your graph again with your reconstructed features, and they usually are less noisy. So now that we understand at a high level what graph networks are and how they function, I want to talk about something that's very related to the topic of this presentation, which is expressiveness. And before I get there, I want to talk about this concept of graph isomorphism. So in mathematics or discrete math and in computer science, two graphs are considered isomorphic if there exists some bijection between the edges in each graph. And I guess this is a very complex or fancy way of saying there is a one-to-one mapping between edges in graph A and edges in some graph B. So you have a bunch of nodes here, and you have a bunch of nodes in this graph. You can see that there are certain nodes with the same connectivity or the same degree, meaning the number of connections that it has for each node. So this node U3 has 3 connections, and it's very similar to this edge V1 that also has 3 connections. And same thing for this graph, sorry, this node U1, it has 2 connections, and it's similar to this V5 that also has 2 connections. And when you do this for both these graphs, you can come up with this sort of mapping. So you have all the nodes in graph A, and you have all the nodes in graph B, and you connect them or you kind of associate one node to another, meaning that it's a one-to-one. So there can't be any collisions, there can't be any clashes. Every single node in this graph will have to map or associate itself with another node here. And the edges and the connectivity, the degree of the graph should remain the same. But how do we know whether two graphs are isomorphic? We can see it visually, but how do we write algorithms that do this? And for that, I want to introduce this thing called the Weisweiler-Leman graph isomorphism test. It sounds very complex, but it's a very, very simple algorithm that can be implemented very quickly. So it is a test for graph isomorphism. It came out in 1968. It was created by Andre Leman and Boris Weisweiler. And it works on the principle of graph coloring. And if you're familiar with graph theory or the basics of graph theory, coloring is simply means I want to label each node with some discrete label or some discrete name or identity. And simply, we want to keep changing these colors over time. We want to keep changing these colors over time, which is why you can call it color refinement. So these colors keep getting refined or changed or updated over time. And I say over here that it works for most graphs because actually in 1969, another group of researchers came up with a counterexample where this test fails. But after that, a whole lot of research has been done to show that the Weisweiler-Leman test, it applies for a lot of graphs, and there are very, very few rare exceptions to this test. So since we know that there are counterexamples, we can say that the Weisweiler-Leman test or the WL test is a necessary but insufficient way to show isomorphism. So necessary means that we need to go through the process to find out whether two graphs are related or isomorphic. But at the end, we can't claim with 100% probability or like 100% probability that these graphs are really isomorphic. And I guess a bit of a fun fact, this WL test is also called the WL graph kernel in other popular literature. So now I'll actually show you how this WL test is done. It's very simple. So suppose we have two graphs, A and B, and we have a bunch of nodes in A and a bunch of nodes in B. Each of them have their own connections over here, these edges, and same for B. So what we do is we start off with a bunch of labels, and these labels you can start off in any way. I've chosen to keep it simple, meaning I've tried to keep it simple by maintaining it as the degree of these nodes. So over here, since this node has 2 connections, that means it has a label of 2. Since this node has 3 incoming connections, I put the label as 3 here. And similarly for this graph, this node has 2 edges, so this label is 2, and so on and so forth for all these nodes. So now after we have labeled all the edges in both the graphs, we want to perform this, this process of aggregating or collecting the labels from the neighboring nodes. So suppose we start off with this top node here in A. It's connected to nodes that have labels of 3 and 3, which is why you can collect them together over here as 3 and 3. When we look at this corner left node with a label of 3, it's connected to 2 nodes with labels of 2 here and here, as well as a node with label 3. So you can kind of collect all these labels from its neighbors, its friends in a way. And same thing for all the nodes in graph A. Similarly, in graph B, this node is connected to 2 other nodes with a label of 3 and 3, which is why we aggregate them like this, and so on and so forth for this graph here. So now I want to talk about something called the hash function, which is very important in the WL test. So the hash function, what it should do is it should take in a multiset. And a multiset, it's basically a set with repeat elements. You can think of it as an array or a list. But mathematically, at the end of the day, it's still a set. And this hash function should take in this set. It could have n different items in it. And you want to return a discrete label at the end. And using this discrete label, we want to update this node's label using this hashed value. And at the end, your hash function can either factor the node's own label, or it can choose to ignore it. So in this case, since this label is 2 and this multiset is 3 and 3, your hash function can either look at 3, 3, and 2, or it can just simply look at this multiset here, 3 and 3, and ignore this node's own label. So for this example, I want to use the sum of the squares of all the labels in the multiset. So that means if I have a node with 3 and 3 as the multiset, if I pass it through this hash function h, I'll be doing 3 square plus 3 square and summing the squares up, and I'll get 18. Similarly, for this node, I have the multiset of 2, 3, and 2. And if I do 2 square plus 3 square plus 2 square again, I will get 17. So you do this for all the nodes in both the graph A and graph B. And at the end, you get this new labeling of the graph. So originally this node it had a label of 2. Now based on this hash function, it now has a label of 18. And you can do the same thing for this node here with the label of 3. Now it's 17. And of course, over here, it's 13. And you do the same thing for B, and you see that it matches, or it has its own new labels for each of the nodes. So now if you do this process of aggregation from its friends or its neighbors again, this node at the top, it's connected to something with labels 17 and 17. So the multiset here collected is 17, 17. And you do the same thing for all the other nodes in graph A, and you do the same thing for all the nodes in graph B. And again, you take these multisets and you hash them. So I just showed you 2 steps or 2 iterations of this WL algorithm. And to generalize it to something that you can program or you can code up, you can think of it as, I want to repeat this color refinement or this color update or this label update k number of times for k iterations. And for all the nodes in A, I want to aggregate it from all its friends over here. And I want to hash these multisets for each of the nodes. And I want to relabel it. So originally this was 2, and then after it became 18. So you do this for all the nodes in A. Next, you do the same exact process of aggregating the labels, hashing the multiset, and relabeling all the nodes for graph B. At the end, you'll get this kind of distribution. Over here, after one round, you get this distribution. You have 2 nodes with label 17. You have 2 nodes with label 13 and one node with a label of 18. Same thing in B, you have 1 node with 18, 2 nodes with 13, and 2 nodes with 17. So you can see that the nodes, the distributions of all these labels, they're exactly the same for both of these graphs. So only when these distributions are not the same, or you notice one label that's off, you can break out of this algorithm and confidently claim that these two graphs are not isomorphic, they're not similar. But at the end of k iterations, if this loop runs perfectly and you come out of the algorithm, you can conclude that the graphs are most probably isomorphic. And there's a very high chance that it is. So what I just showed you right now is the WL test. It's an iterative label update algorithm, and it's a polynomial time solution to graph coloring or graph isomorphism. So at the end of these k iterations, you'll get some distribution. The top nodes have A, and some nodes have a coloring or label of B, and some nodes have a label of C, and same thing for P. And at the end, if these distributions keep matching at the end of k iterations, you can say that both of these graphs are isomorphic. So now that we understand the concept of the WL test, I want to draw some parallels. I want to show you how similar it is to the concept of a graph neural network. So the process of aggregation stays the same, right? You have a certain node and you have a bunch of neighbors. You want to collect the labels or the features from all of these neighbors or your friends, and you want to perform some function on it. After that, your readout function is the same as your hash function. You take all of your neighbors' embeddings or your features, you perform some transformation, get the message, and you want to update this target node's labels based on this transformation. So the WL test and graph neural network, they have the same exact processes happening. They have neighbor aggregation, and they have some kind of readout operation that updates the features or updates the labels of each of these nodes in the graph. And of course, you can do the same thing for your edges. And now that we understand the process of the WL test, and now that we know that it's very similar to the graph neural network, I want to go through the concept of GNN expressiveness in a lot more detail. And this is the actual, the crux or the gist of the topic that I wish to show you today. So simply put, GNN expressiveness is the ability of a GNN to distinguish between two non-isomorphic graphs. So suppose you have two graphs that are not similar, that are non-isomorphic. You want your graph neural network to process them in such a way that it looks at them as two separate graphs. You don't want the graph neural network classifying both of them into the same thing or the same category at the end, purely because these graphs are different from each other. And we know that as the person designing these experiments. So I showed you at the start, I showed you this process of message passing. Simply put, message passing is I want to collect all my neighbors' features. I want to transform them in some way to get a message. I want to take this message and my own features. I want to transform both of them together again. And I want to update my features to move on to the next layer or to move on to the next iteration of message passing. So the process of aggregation is a very tricky problem because through research, we found out that a lot of these popular aggregation functions are not very expressive. They result in very poorly expressive graph neural networks. So aggregation functions are something that collect all your neighbors' messages or neighbors' features and perform some transformation. And simply these transformations can be the maximum of all your neighbors. It could be the minimum of your neighbors. It could be the average of them. So you add up all the neighbor features and you average them, or you divide by the number of neighbors. So researchers found out that the maximum aggregator, meaning taking the max of all your neighbors, when you use the max aggregator, your graph network cannot tell apart two different structures. So if you look at this left example here, both of these graphs, you can clearly tell that they're non-isomorphic. They're not even the same. This one has 4 nodes and this one has 3. But if you apply the max on these nodes, and suppose red is the max here, of course, green is lesser than red. So your max aggregator will give out this value for this left graph. And over here, since you're only comparing between this green node and this red node. And since we know that green is greater than red, in this situation, it'll return red again. And at the end, both of these graphs give out this red feature or this red node as the maximum, but you can't tell them apart because these values are all the same. So your graph network will think that this graph is the same as this graph, purely because this aggregation function gave you the same value. Similarly, on this right example here, your mean and max can't tell apart these graphs. So on this graph here, when you take the average of this green and red, it'll give you some other value. And at the same time, if you take the average of all of these 4 nodes, you get the same exact average. So since this graph gives some average x, and this graph here also gives the same value x, your graph network will think that both of them are the same. And this is very problematic. And of course, it's very trivial to see that the max aggregation will also fail here, because at the end, it will also give these red values. So message passing, when you have these situations here, structural information is it's not captured well. So of course, this graph structure is very different from this, but your graph network will think both of them have the same structure. And the same issue with this graph here. So I want to talk about this concept of higher order structures. And usually in vanilla graph neural networks, you deal with single nodes on their own in isolation. But of course, looking at single nodes, you encounter these problems where your simple maximum and mean aggregators don't work. In that case, we want to look at something more complex. We want to look at something with a higher order. And in that case, we can look at things like rooted subgraphs. So if you have a single node, you can look at all the neighbors connected to it, and you can look at the neighbors' neighbors. So in a way, that itself is a very large subgraph. You can look at k-hop neighborhoods, meaning it's another term for my neighbor's neighbors. So if it's a 2-hop neighborhood, I not only collect features from my immediate friends, I collect the features from my friends' friends as well. And you can look at something more casual, something more trivial, something like the pairs of connected nodes. So if you have 2 nodes connected with each other, you can consider that pair together as one meta node or one giant node on its own. So I want to conclude that these higher order structures, when you use them, rooted subgraphs, k-hop neighborhoods, tuples of connected nodes or pairs, your GNNs become more expressive because you're looking at a lot more nodes, and looking at more nodes introduces a lot more complexity. And 2 graphs, if you look at the higher order structures from both of these 2 separate graphs, they look very different, and it helps the GNN tell you that both of them are different, which is what we want at the end. So when you have graph networks that are very expressive, these graph networks are better at assigning node embeddings or features for the next layer as input. So when you are going through the graph neural network layers, your GNN can tell apart the structure of the graph. So, and if you think about it in the embedding space, this could be some RD space where D is the embedding dimension. The 2 graphs, they won't share the same point because your graph neural network puts one in some corner of the space, and your graph network puts the other graph in some other corner of the space, purely because they're different. So I showed you this thing called the WL test. Next, I want to take you one step further and share with you this concept of the WL hierarchy. So the WL test, it's a very simple way of testing for graph isomorphism. So at the end, we want something that's even more powerful than this WL test. We wanted to do the WL test not only on single nodes, we want to do them on these higher order structures. We want to do WL test on rooted subgraphs. We want to do the WL test on k-hop neighborhoods. And we also want to do them on the pairs of connected nodes. So, which brings us to this concept of the KWL test. So K is an integer, it could be 1, 2, 3, 4, any integer. And all this means is that we're looking at different orders of these higher order structures. So when I have the one WL test, that is very similar to the WL test that I showed you. One meaning I only look at one node and its immediate neighborhood. Two means that I look at the neighborhood and its neighborhood, and so on and so forth. So one WL graph neural network and two WL networks, they're more or less the same. We're looking at the neighbors or the neighbors' neighbors. And at the same time, when you look at higher values of K, like 3, 4, 5, I want to show you that the KWL GNN is weaker than the K+1 WL GNN. So this means that there are graphs on which your KWL network fails, but your K+1 WL network succeeds, but not vice versa. So that means that the higher this value of K, the more expressive my network. And together, all these values of 1, 2, 3, 4, 1 WL test, 2 WL test, and 3 WL test, and so on, they make up this thing called the WL hierarchy. And they indicate the expressiveness of the graph neural network. And now I want to show you a visual depiction of what exactly I mean. So your 1 WL expressiveness, it's pretty standard. You have a bunch of nodes in a graph and you look at their immediate neighborhood. So this is like your one hop neighborhood, your immediate friends. And you want your 1 WL network to show or tell you that both of these graphs are not the same. Even though they share the same structure, they're not exactly the same. Next, we have 2 WL expressiveness. So I look at my neighbor's neighbors. So this yellow node, it's connected to red and green, which you can see here. This red node, it's connected to this yellow and green node, which means that I'm looking at my neighbor's neighbors. And same thing for this green node. The green node is connected to yellow, red, and blue. And so I'm looking at a more complex structure, a more higher order structure. So this is what I meant by higher order structures. They are more complex. And at the end, with your 2 WL network, you want your network to tell that these graphs are not the same. These subgraphs are not the same, even though they share a similar structure. And finally, we have 3 WL expressiveness. So we're looking at a 3-hop neighborhood for this node over here and this node over here. And you can see that they share a very similar structure. If I completely remove the colors from all of these nodes, both of these structures would be the exact same. But you want your graph network to treat both of them different, purely because both of them are 2 different nodes. So now that I showed you the different hierarchy of the WL test, I want to show you the importance of why are we using this WL hierarchy. So the GNNs, at the end of the day, they only look at features, the node features. So in a social network graph, this could be name, age, gender. For a molecule, it could be its different atomic properties. So they don't look at their exact labels. They don't look at the numbering. There's no ordering for a graph because even if you shift a node slightly to the right, it's the same exact graph. So if you use poorly chosen aggregations like your mean and your max, your subgraphs will look exactly the same. Your structures over here from 2 different nodes will look exactly the same. And without any features, if I removed all the colors, your GNN would treat both of these the same way, and you would embed them the similar way or classify them as the same thing. Even this could be an oxygen atom and this could be a hydrogen atom. But at the end, since both of their structures are the same, your graph neural network will say both of them are oxygen atoms, which isn't the case. So this is the failure case for a lot of your vanilla graph neural networks. And this is a problem that the expressiveness community is actively tackling. It's actively looking at this concept of expressiveness and trying to improve the expressiveness of your GNN. So so far we've talked about GNNs that are at most as powerful by the WL test. So that means they are very close in performance to the WL test in telling 2 graphs apart, at discriminating 2 graphs, but they're not as good. So now if we actually want to improve the performance of these GNNs, how do we make them as powerful as your WL test? How do you make the WL test the lower bound in a way? And for that, it's a very simple addition to your vanilla graph neural network. It has to do with your aggregation function and your readout function. So just for a bit of a recap, aggregation is something that takes all your neighbor features and combines them in some way. Readout function is something that takes this aggregated message, it takes the node's own features, it combines them in some way, and it updates the features of your node. So research has shown and more specifically, this paper Stu et al. In 2019, they proved that to make a graph network as powerful as the WL test in discriminating between two graphs, you need to make your aggregation and readout functions injective. So injectivity, it's a concept again in discrete math. Previously, for graph isomorphism, we spoke about the concept of bijectivity. Here, it's another concept of injectivity, and all it means is that suppose we have two sets, X and A and B, and Y equals fx. For every value in your B, every Y value here, there is only a single value in X that can result in this Y. So, which means that there are no collisions happening. For every Y in this set, there's only one unique X that can cause this Y to take, or this Y to be the result. So in when we're looking at it in the eyes or the lens of a graph network, we want these aggregations and readout functions to be injective. And this means I want to map my multiset. So that means after I aggregated them all together, I want to take this multiset and map it to a unique value. So this means this multiset 3, 3 will give me some value A, and this other multiset 2, 3, and 2 will give me some other value B, and this other multiset 3 and 2 will give me some value C. All of these values A, B, C are unique, and you can see that this hash function or this readout function, it results in very unique values. So once we achieve this, when we make injective readout functions, your graph neural network becomes as powerful as the WL test. And because of that, it can take the structure of the graph into consideration. And it's a very huge improvement on your basic message passing. So when I say that I want to use my WL test, or want to be as powerful as my WL test, I want to say that I want to use my one WL test as my lower bound. So that means if I have my full multiset, so I have these nodes, all their features, when I collect them and pass it through a readout function, I want this node to give me a unique value. And at the same time, for this node over here, I want to take all its subgraphs, all its neighbors, all this whole multiset, put it through the same readout function, and it should give me the same. It should give me a different value. And by ensuring that through the injective property, your graph network becomes as powerful as the WL test, and it becomes a very good GNN to use. So your GNN expressiveness, when we don't achieve this, right? Or I want to take you through some consequences of not achieving it. On the one hand, if you are doing some social network analysis, you want to see which friends are connected to which other people. You want to do some user, who is this person connected to? Your GNN won't be able to tell apart triangles or clicks or bridges in your graph. And at the same time, if you're working with chemical data, if you're working with molecules, something like this, you wanted to consider the structure here. If you consider your carbon atom here and your hydrogen atoms here as nodes, you want to be able to take this structure and do something with it to show you that this molecule is very different from some other molecule that looks very similar. So if you have very poorly expressive or inexpressive GNNs, you end up doing well on some data sets, and you end up doing very badly on other data sets. And we don't want that. We want GNNs to be able to do well on almost every data set. Otherwise, why would we want to use them? So based on what all I've shown you, I guess long story short, the conclusion is that expressiveness of a GNN, it's dictated by the expressiveness of your aggregation and readout. And by expressiveness, I specifically mean the injectivity of this aggregation and readout functions. And once you achieve that, your GNN can be expressive. It will be working way better than your vanilla GNN that uses vanilla message passing. So now that I've shown you a quick look at what expressiveness is, how do you measure a network's expressiveness, I want to take you through some notable works that have come out over the years that have really caught my eye and are really pushing the boundaries of GNN expressiveness research. So as to what exactly has been done to bring about this change or improvement, a lot of solutions have come out that look at a lot of things, and they have a lot of variation over vanilla GNNs. Some of these improvements, they work on higher order structures. So instead of working on only single nodes and their immediate neighborhoods, immediate friends, they work on subgraphs, meaning I want to look at my friends' friends as well. I want to remove some edges that I think are useless. I want to create these subgraphs and look at them. I want to look at graphlets, meaning I remove some nodes here and there. I remove some friends from each node, and I want to consider those subgraphs. And of course, I want to consider this thing called the ego graph, which means I want to look at the immediate neighborhood of a single node. So some other papers have introduced this concept of equivariance, which means if I take my graph nodes and I jumble them up together, if I take one node from the right and push it to the left, or if I rotate the nodes or rotate the graph, all the nodes retain their labels. Nothing about the graph should change except the way it looks if you plot it somewhere. And finally, if you are familiar with the concept of positional embeddings, maybe from attention, it simply means that we want to index them or we want to fix them in some RD or RN space. So there's a lot of exciting work being done in structural or positional encoding. So in terms of the specific papers that I want to go through, I will be covering 3 of them. The graph isomorphism network, the equivariant GNN, and the equivariant subgraph aggregation network. So all of them do sound complex, but all of them introduce very, very simple changes to your message passing neural networks, and it really blows the competition out of the water. And all of these works and a lot more, they introduce innovations in the way they design their aggregation function or update function. They do a lot of innovations in the structural encodings or the positional encodings of all of these nodes in some RD space. And of course, they look at these higher order structures like graphlets, subgraphs, and ego graphs. So first, I want to begin with the graph isomorphism network by Su et al. This was the same paper that proved that adding injectivity to your readout function will improve expressiveness. So as I mentioned, this paper proves that injective aggregations and injective readouts result in more expressive networks. So you have your readout function, which is basically your multi-set hashing function, if you remember the WL test. And what the paper does is it substitutes or it adds 2 multi-layer perceptrons or some complex neural network that not only works on the neighbors, but the node itself, and it combines them in some way. And I'm sure as machine learning practitioners, you may have heard of the universal approximation theorem, which states that a neural network or a complex enough neural network can approximate or simulate any function, any real valued function. And of course, they use the sum aggregation because through their experiments, they see that sum aggregation works better than the mean and max. So what they do is that they show that this graph isomorphism network, the GIN model, is the same as the WL test, purely because you can model their readout function to the WL test. So you have your neighbors here. It's going through some multi-layer perceptron, some hash function. And of course, you have your own nodes labeled, target nodes labeled, and you again perform some function on it. You can abstract this or generalize this further. You can replace this NLP with any generic hash function, and you can write it like this. The node's next features or the next label is the hash of the node, of the target node's label, as well as the hash applied to the neighbors. So they look very similar. And because of that, they claim that GIN and the WL test have the same expressiveness. And the results go on to show some very beautiful improvements compared to vanilla GNN. Next, I want to take you through the EN equivalent graph network. It's by Satoris et al. And it came out very recently last year. So what they do is they introduce this concept of equivariance. So suppose I have any generic graph, it has a bunch of nodes, has a bunch of edges. If I rotate the graph, by 90 degrees, or I take a node and I shift it from some left corner all the way to the right corner, you don't want the graph to change. At the end, it's representing the same graph. It's representing the same entities. It's representing the same connections or relationships between your nodes. So what the EN equivalent GNN does is that it introduces rotation and translation equivariance. So it means that you can do whatever rotation or translation to your graph, and at the end, your predictions should not change. And for that, they use positional embeddings. So for example, in a 2D graph, when you have an X and Y coordinate, you have two dimensions. You have an X dimension and a Y dimension, and you can represent any point using X comma Y. Similarly, your nodes in a very complex graph, all their features, you can think of them as feature vectors. And if the vector has some D dimensions, you can plot it or kind of project it in RD space. And you can use the exact coordinates of those nodes in the message passing step. So over here, you have your features of the nodes HI and its neighbor HJ. And you have the exact position of them, XI and XJ. And of course, if you have some edge features, you can also add them here, but this is optional. And you do this function and you get this MIJ. And this is the message that comes out of this connection between node I and its friend node J. And again, you use this function to update the positional encodings over time as well. It's very similar to the way it operates in transformers or attention-based models when you have positional encoding. And at the end, you have these neural networks F, G, and H. When you put them all together, you are able to achieve this rotation and translation equivariance. So now, not only do we have the features, but we have the exact positions of all the nodes in my graph. So it gives me two things to differentiate a graph. So even if two nodes have the same features, they will definitely have two different positions in RD space, which means that I can use one or the other of these items to differentiate them. And it'll give you different outputs if you use some injective readout function. So suppose I have this very simple graph with these nodes, 1, 2, 3, and 4. These nodes have their features H1, 2, 3, and 4. And they also have their position. Suppose I plotted them in some 2D space. They have their own X comma Y positions for each of these nodes. And you include both of these H features and your X positional encoding into these message passing steps. And with that, your network becomes so much more expressive. Finally, I want to take you through this paper called the Equivariant Subgraph Aggregation Network. This paper is very special because I'm basing my own research on it. And it's also called the ESAN, ESAN network. And it's by Bevilacqua et al. And again, it was released very recently last year. So sometimes, as I said, your WL test is not perfect, right? You can never claim with 100% confidence that two graphs are non-isomorphic or isomorphic. So not all graphs can be distinguished by WL test. And if you want to work it out on your own time, if you take both of these graphs, both of them are not isomorphic, but they'll give you the same distribution of your colors for each of these nodes. Which is why ESAN says, if the whole graph can't be distinguished by the WL test, let's look at its subgraphs instead. And subgraphs are simply the same graph, but you remove some edges, remove some nodes, and they look very similar, but you can think of it as a bit of damage done to this. So what ESAN does is it considers this thing called the bag of subgraphs. So for example, you have this whole graph here, and graph A and graph B. The subgraphs of them are, you can think of these two as subgraphs. This is another subgraph, and this is another subgraph here. When you consider all three of these groups together, and you put them together in one basket, you get a bag of subgraphs. So your ESAN network looks at them, and it passes all these subgraphs. It passes it through an equivariant GNN, something very similar to the eGNN that I showed you. And there are, of course, these different subgraph selection policies, meaning if I have this very whole graph here, how do I generate all of these subgraphs? You can either then do it by randomly dropping edges here, randomly dropping nodes, or you can just have a very greedy way of dropping them. Either way, you can take all these subgraphs, you can pass it through this network, and at the end, it produces these graph embeddings. So if you remember the starting half of my presentation, I mentioned what can be done with these GNNs. Whole graph classification or whole graph regression is one of them. And ESAN is one such network that does that. So specifically this equivariant GNN, they use this model called DeepSet. It's a very popular network. I urge you or recommend this paper to read. So suppose all of these are the different subgraphs from this graph. You feed all of their adjacency matrix, all these subgraph features one by one. You feed them into this DeepSet and graph neural network. You process all of them together, and you get this final graph embedding. So even if you shift this yellow and blue subgraph, if you swap them, the order doesn't matter because we're using an equivariant GNN, and you can transform them, so you can translate them or rotate them and swap them. It's not going to have any effect. So by doing this, you can achieve some very high expressiveness scores. And this paper adds some very beautiful proofs to show you why this model is very expressive compared to a message passing neural network. And with that, I want to end off with some final comments about the future of expressiveness research. It's a very new field. It's being done very recently. A lot of work has been conducted, and a lot of researchers are now gathering into this field because they found out that vanilla neural GNNs, they just aren't up to the task. They work for some data sets, but fail miserably for others. And we want to fix that. So I guess the sad thing that we need to address and acknowledge is that the higher the expressiveness of a GNN, so I'm talking about 2WL, 3WL, when you do that, you're looking at like neighbors, and even their neighbors, right? These very, very dense subgraphs, these very high order structures. When you're considering all of them, you need to use a lot more computational power. So your 3WL GNN is going to be way more expensive to run because you're looking at very large subgraphs centered around all of these nodes. And in fact, 3WL is the highest that the community has reached so far. And I'm pretty sure that there's a lot of research going in to improve this standard. Next, I showed you this ESAN paper that looked at subgraphs. So far, recently, a lot of works have come out where they do some kind of subgraph processing, where they do very fancy things with subgraphs to tell apart two graphs. And we found out that it's very nice because subgraphs are very sparse. They don't have that denseness or that density of the whole original graph, which makes them very quick to process. And it allows for faster computation, pre-processing, all of that. Now, and next, I mentioned that the sum aggregation, the Su et al. Paper that introduces the graph isomorphism network, they noticed that the sum aggregation is the best aggregator compared to mean and max. It introduces a lot more expressiveness because the sum is injective. It gives a very unique mapping between the multiset of neighbors and some unique value to update the nodes labels or nodes features. And finally, another observation is that a lot of research is going in to use positional encoding, like the ENGNN, like the equivariant GNN. It makes use of these positional encodings. And the research has shown empirically that introducing these positional encodings can really help improve the expressiveness of networks. So all these 4 points that I brought up, they form a very small niche of expressiveness research. There's a lot more going on behind the scenes that I'd love to share with you. And there's a lot of work that you yourself can explore on your own. And I really recommend getting into this if you feel that your GNNs are underperforming and you want to squeeze some more performance from them, given that you have sufficient computation and time resources. And with that, I thank you so much for your attention. I understand that it's around 6 p.m. or 7 p.m. in India. If you have any questions, I'd love to stay behind and answer them. But with that, I come to the end of my presentation. Thank you. If you want to contact me or reach out in terms of questions or doubts, please feel free to reach out through these avenues. Yeah, you can get my email through my website, or you can reach out on Twitter. Thank you. Dr. Rakesh, back to you.
Yeah. Thank you, Rishabh. Yeah, your talk is very nice. Yeah. So I hope that the participant would have understood, the graph, the way you have represented. So it will be very helpful for them. And the way you have represented, like all the literature work, are very appreciable. So once again, I would like to say thank you for accepting our invitations and delivering this wonderful talk. So I hope that the participant will try to reach you. Okay. Thank you. Thank you, Rishabh. Thank you very much. So participants, if you have any questions, so you may ask. Please raise your hand otherwise. Yeah.
I have a question from Mr. Swaroop. Would you please unmute yourself and ask the question, please? Mr. Swaroop Roy. Or you can type it to me in the chat as well.
Yeah.
If it's convenient.
Can you hear me?
Yes, yes.
I can hear you, yeah.
Yeah, hi, Rishabh. It's a full, nice talk. It's a full package that you have delivered. I really liked your illustrations and all. That's fine. Yeah. So though I am also new in that area of GNN and all, and you have really discussed something new. I'm also stuck into that and to grow some interest into that, the problem of WL and isomorphism. Now, I have one doubt, doubt in the sense, throughout that talk, I could not able to find out where is the learning parameter, which learning parameter that has been used in that problem. Though you are using the neural network, where is the learning parameter? Is there any learning parameter?
Yes, definitely. There are a lot of learning parameters that go into graph neural networks. And
hello, can you hear me?
In fact, I guess a fun fact
hello,
is
am I
that.
Audible?
Hello, yeah,
hello,
I can hear
audible?
you. Yes.
Yeah, am I audible?
Yes,
hello?
yes, you are audible.
Hello.
Yes,
hello?
sure, you are audible.
Hello. Hello.
Maybe some internet connection.
I guess the question was whether there are any learning parameters that need to be trained over time. And the answer to that is yes. And the fun fact is that it's quite low in terms of the parameter count. It makes the training a lot faster. So over here in this graph isomorphism network, I mentioned
Satya,
that.
can you unmute? Some participants want to ask question. Can you unmute?
Yeah. So I mentioned that over here, the graph isomorphism network, it makes use of these multi-layer perceptrons. These multi-layer perceptrons, they have their weights inside, and using regular gradient descent optimizers like SGD, vanilla gradient descent, Adam, and anything that you use, you can actually train this in an end-to-end manner. All your node features, you can stack them all up to form a matrix, and this matrix, you can pass it into a multi-layer perceptron, and you can process it the same way you would with regular data like MNIST or any matrix based data. So, and you can train it end to end using gradient descent. And over time, your network parameters get updated or optimized towards global minimum. So I hope that answers Mr. Swoop's question. Next, I have a question from Dr. Christina.
Yeah, hi Rishabh, I hope I'm audible.
Yes.
Yeah, very interesting talk. Thank you for taking us from the basics. So I have one question. You have mentioned about the WL test for graph isomorphism. So we have a couple of other techniques as well, like the DFS code or other canonical labeling techniques. So how does these two relate?
So in the, I guess, the mini field of expressiveness, the WL test is way more popular purely because you can represent all the operations of a GNN using similar operations in the WL test, right? So in this slide, I show you that, sure, you have your MLP and whatnot. You can swap out this MLP with a hash function and you have the same process of aggregating your neighbor's features or your neighbor's labels and performing some transformation on that using your hash function. And it's very, very similar to what the WL test does and what the GNN does. The thing about the DFS code or any other algorithms or isomorphism algorithms is that you can't really represent them using typical GNN functions like aggregation, message passing, anything like that, which is why WL is the best algorithm for reference. I hope that clarifies.
Yes. Thank you so much. And also, since you are working on transformers as well, I was just curious to know how transformers could be applied on graph data.
Actually, there's quite a lot of exciting work being done in using transformers and more fundamentally the attention mechanism, self-attention, or all these complex forms of attention, using them on graph data. So suppose, actually, I can give you like a rough example. I don't have it in my slides, but hold on. Suppose I have this graph here, and suppose I have, I zoom into this neighborhood. I can use this form of graph attention, where I look at the features of this yellow node, orange, dark purple, and red. All the neighbors, I can look at their feature, and using attention, I can score all of them between 0 and 1. So each edge can be scored. So if that edge score is closer to 1, it means that my neighbor's features are way more relevant to this target node's features. And if the score is closer to 0, that means we can more or less ignore or neglect this node over here. So after that, you weight all of these features using this attention scores for each of these connections, and you add them all up and use them to update this target node's features. So the paper is called Graph Attention Network. It's called the GAT. It's by Velikovich et al. And it's very popular. So I'd suggest reading that. On the other hand, there's this thing called the Graph Transformer. It's another very popular, Graph Transformer, which is another very popular work where they try to use this concept of graphs and show similarities between a transformer. Actually, a very good friend of mine from Cambridge, he has written this very in-depth article on the gradient, which is a very famous, I guess, publication by Stanford University. He published this article called Transformers are GNNs. I think this should be somewhere soon. Yeah. It's called Transformers are Graph Neural Networks, where he shows that he takes you through a bit of NLP basics. He shows you all the equations of a GNN. He shows you all the equations of a transformer, and then he shows you that they're very similar. So that's another interesting work that you can read, the Graph Transformer paper. Hope that clarifies the second question.
Yes, so in that context, has there been any works on expressiveness of graph transformers as well?
I'm the field, as much as I say that it's new, there's actually quite a lot of work. I mean, as with any machine learning subfield, there's a lot of work that comes out very quickly. So even though I might not be aware of immediate works that come to mind, I'm sure there are people experimenting on graph transformer expressiveness. And the thing about graph transformers is that I'm pretty sure they make use of these positional encoding as they do with regular transformers. Hopefully that goes on to improve the expressiveness and I guess applicability of these networks.
Thank you so much. Thank you.
Yeah, thank you. Any other questions?